Hi everyone, I'm happy to be here and be able to tell you a bit about what I've been working on for the last 2 years, and that's A/B testing. I really like this topic because it's probably the most impactful project I have worked on. Why? Well, it's in the core of innovation in every large company we have worked with. If you do not A/B test, then you don't really know if the machine learning models that you have created or your user experience tweaks really work. And so I think that everyone, or almost everyone, should be doing A/B testing. So if you don't know what it is, don't worry, I will explain it soon. I also like this topic because it involves a lot of interesting problems, and one of them is bootstrapping. So obviously the topic of this talk is mainly bootstrapping, what it is, why it is useful, and how to do it in Spark to improve A/B testing. But first, let me tell you a few words about myself. So I'm a data scientist now, but the path that brought me here was through an interesting detour, which is now actually paying off. So I studied computer science, but then I went into academia and I got a PhD in neuroscience/psychology. I was doing experiments on human cognition, putting people into scanners, all this fancy stuff. And in the process, I learned a lot of statistics, how to analyze data from my experiments, and also how to design experiments. And A/B testing is experiments. In some ways simpler, in some ways more complicated than what I was doing by then. So after some postdocing, I left academia and went back to industry, where this combined background is now quite useful. So now my current focus is on inferential statistics, machine learning, pipelines, ETLs. I use Apache Spark with Python, R, and the types of problems I have worked on range from A/B testing, recommendation systems, search engines, and so on in various industries like e-commerce, social media, insurance, and so on. And I come from a company called Datacentrics. And as you can read in the middle, we are making data science and machine learning have a real impact on organizations. We have many scientists and engineers in several tribes, which you can see on the left, and they focus on various industries and use cases. For example, personalization in banking and insurance, computer vision apps for analysis of shelves in stores, recommendation systems in e-commerce. But in all of these solutions and products, we need to do A/B testing to know that they really work and bring benefits to our customers. So we use A/B testing internally for our solutions, but also we implement it for clients who want to bring their A/B testing to the next level. So now the agenda of this talk will be, I will finally tell you what A/B testing is, and in particular, what factorial A/B testing is. Then we will briefly go into the analysis of such results. And the main portion of the analysis that I will be talking about is this mysterious word bootstrapping. So I will explain what bootstrapping is, how to do it in Spark. And finally, we will look at some performance considerations. So finally, what is A/B testing? Wikipedia says it's a user experience research methodology which consists of a randomized experiment with two variants, A and B. It includes application of statistical hypothesis testing and determining which of the two variants is more effective. Well, to put it simpler, let's say that you have a website and you want to change something, for example, color of a button or something in the backend. And you only show this change to a portion of your visitors and measure some KPI like conversion rate and see in which of these two groups the metrics are better. So you have typically some control version and some experimental version that you expose your visitors to. Why would you want to do A/B testing? Well, it's the only way to improve your KPIs consistently without relying on guessing or intuition or the highest paid person opinion, the hippo. The evidence is always better than anyone's opinions, because it turns out that most of the tested ideas are actually incorrect. They don't bring value, but you don't know it if you don't test it. And how do you do the testing? Usually you do isolated tests. That means you divide your traffic into parallel lanes so that each user is exposed to just one variant. So you can run such tests in parallel or one after another. Yeah, that's all fine, but these tests prove to be limiting if you really want to do it seriously, if you really want to test all ideas as you should, because you can only run few such concurrent experiments, or they take a very long time. On the right, you can see a chart from Microsoft experimentation platform, from Bing specifically, and in 2003, which is where the red text points to, something happened. So this chart shows the number of A/B tests that they were able to perform per week, I think. And so until 2013, there was a small trend. The number of tests that they were doing was rising, but then something happened and the amount of A/B tests they were doing skyrocketed. And what happened was that they introduced an experimentation platform that used so-called factorial design of experiments. In detail, it's a bit more complicated than what I will describe, but in a sense, it's this. So let's say you have two tests, test one and test two. Test one tests whether you want to display some text in original black or you want to change it to blue font. And test two tests some old current recommendation engine against a new one. And basically, you expose your users to both of these tests. Actually, so when a user comes, you first flip a coin for the first test, whether they will see the black or the blue test. And then for the same user, you flip a coin again and decide whether the user will be exposed to the old or the new recommendation engine. And you can do this for dozens of tests, with some caveats, but in a sense, that's this. And this is called a factorial design of an experiment. So you have to cross these tests orthogonally. There must really be a random allocation. And therefore, each visitor gets assigned into all the tests. And this will allow running dozens of simultaneous tests if done correctly. Because then you will be testing all of these tests on all the traffic that you get. And therefore, you will get faster results. Okay, so let's say you have collected some data from the experiments and now you want to analyze them. How do you do that? What you often get in some products for A/B testing that you can buy, some services, is results of this kind. Version B has a statistically significant effect on conversion rate. P-value is 0.04. Well, what does this mean? And surveys show that actually not even statisticians can always interpret this correctly. What this mysterious p-value means. What is statistical significance? And business users, they don't get it. They think that it's something important, but they don't know what exactly. So what you ideally want is something along these lines. The version B increased the conversion rate with some probability, and most likely by that much with some confidence interval. Yeah, so you quantify both the most likely effect size, how much it probably helped, and also the uncertainty that the true value of this improvement can be in this confidence interval. And it can even be negative with some probability. And then you can also show nice density charts like that, or box plots, etc. Yeah? So here on the left, we can see the possible distributions of the possible values of the conversion rate in the control and the B group. On the right, you can see the possible differences, the uplifts. So it's somewhere around 1.8%, but it can be even negative, but most likely it will be positive. So in my opinion, this would be, even though this might not be statistically significant, it might be still a good business decision to implement this. If you consistently implement tests with such probability, then you will in the long run benefit from that. But that depends on your policies, on your decision making under uncertainty, which is quantified here. So you need an estimate of of not just the effect size, but also the uncertainty. So how do you get it? So the effect size we can estimate. We estimate it using Apache Spark because we have typically big data, like millions of impressions, conversions, and so on. So we use GLM, Generalized Linear Models, in Spark, and the model specification is whether there was a conversion, that's the target, per allocations to the different tests. And the product there means that we can also look at interactions between those tests. And we use a binomial GLM with the logit link. Basically, that means logistic regression. But you can also use different GLMs for different types of metrics. And how do you quantify the uncertainty? Well, unfortunately, Spark doesn't always produce standard errors, which is a metric of uncertainty. So you can get it using this process called bootstrapping. And bootstrapping is a way to estimate distribution of some statistic, for example, these estimates, the effect sizes. And it's also said that bootstrapping is a poor man's Bayes. So Bayesian inference, that's often talked about in A/B testing, and really it's a good approach, but often infeasible, especially if you have really big data, then it's hard to do Bayesian inference. So this is a poor man's Bayes with non-informative prior, which is often desirable anyway. And then you can get distribution using bootstrapping that looks like this. So what is bootstrapping? It's very simple, actually. You just iterate many times, hundreds of times, ideally thousands of times if you can afford it. This simple process, these two steps, you just randomly resample data with replacement, and then you estimate some statistic. That means you fit the model and get the GLM coefficients. In Spark, the code can look like this for the one iteration. You just sample with replacement, fraction 1.0, that means all the data. Then you fit some model on the data and extract some stats, some statistics, and save the coefficients. And you do this many times, and you always keep the stats. Here, the model fit will execute a Spark action, right? So that can look like this on the right. Many Spark jobs. In each Spark job, you'll have some stages with some tasks in them. So this process is parallelized, right? This one model fitting and the resampling, that's parallelized over the cores in your cluster. But how do you do bootstrapping efficiently in Spark, given that bootstrapping is also a so-called embarrassingly parallel problem? The individual iterations do not depend on each other. So you can run them simultaneously. But how to do that? Because Spark parallelizes tasks of the resampling and model fitting within one iteration, but you need to, if you want to scale this computation, if you really want to hundreds of iterations, then you need to scale this. You need to parallelize this parallelization, basically. You need to run many instances of this model fitting in parallel. And how to do that in Spark? So that was the question that I was solving, and the solution was in a way simple, but maybe a bit involved for those of you who do not have experience with Python and Spark, and it's multi-threading. So let's go into this in a bit more detail, perhaps. So you need to prepare, you need to put the bootstrap iterations into batches. So let's say you have, I don't know, in this case, 12 iterations. In the real life, you would have, for example, 2000. You would put them into batches. In this example on the right, I have 4 batches. Okay, so you can see that in each batch, I have 3 iterations. And so each batch consists of sequential iterations. So these iterations will be run sequentially. But I prepare many of them, of these batches, that will get executed in parallel so that their tasks can go in parallel to the different cores in the cluster. Because each iteration will perform a Spark action. That means it will produce some tasks that will need to go to some cores. And you need to prepare the data in such a way that the stages in those iterations will have fewer tasks than you have cores in the cluster. So you have to repartition your data and size the cluster in such a way that you can actually fit these batches next to each other. I will talk a bit about that in a moment. Then once you have these batches prepared, then you can submit them using Python multithreading. And they get executed, these iterations one by one in all these batches in parallel. And the tasks from these iterations will get scheduled in a first in, first out manner or in a fair fashion, depending on the setting of your Spark application to the executors. I don't think that it really matters which of these two approaches you use. So within one iteration in this picture, you can see that I have, for example, one stage. In reality, you'll have probably more stages, but let's look at one stage. And in this stage, I have sized it in such a way that there's only 4 tasks. And I create so many batches that these 4 tasks will be pushed on average to just 2 cores. So first, let's say task 1 will go to core 1, and task 2 will go to core 2, then task 3 to core 1, task 4 to core 2. And similar things will be happening in the other batches and in the other iterations inside those batches. And so let's say that batch 2 will push the tasks to cores 3 and 4 and so on. And in the end, it doesn't really matter. It's not always batch 1 pushing to cores 1 and 2, but it doesn't matter. You have enough cores to satisfy all the needs of all the different batches that are running in parallel if you size those tasks and the numbers of batches correctly. So now to illustrate this in code, in Python, just briefly, we first need to prepare the batch sizes. So in the first 3 lines, I just take the desired number of iterations and the desired number of threads, and basically figure out how many iterations I need to have in each batch, and I create the list of batches. So let's say here I will create the batches variable will be a list of size 4, and in each of them I will have reps, some batch size, some amount of iterations that I want to run in this one batch. And then using multithreading, using the thread pool executor, I can run n threads workers, for example, 4 workers in this case, and I will submit a function called run batch here, and this function run batch will run all the iterations for this one batch. So the parameters of this function are the data frame, the df, the model, and then the number of repetitions, number of iterations for this one batch. We let it run, and then we collect the results. So we also need to think a bit about performance, because we don't want to waste resources. What use there will be to do all this exercise if in the end it doesn't help you with how long it takes for all this to run, to finish. So one question is, how many parallel batches, how many threads do you need? And there's a simple computation without any rounding. I omitted roundings and numbers of cores that you actually have. And basically it's the numbers of cores divided by the numbers of tasks in one stage in one iteration. And so that would be, in my case, 8 divided by 4, because I had 4 tasks in one iteration, times some constant, some number of tasks per core that you want to have. How many tasks you want to push to one core at any given time. And number of tasks depends on the sizes of the task. So you want to repartition the data so that one task has something around 100 to 200 megabytes. not kilobytes, not gigabytes. And the number of tasks per core, that's an empirical question, what is best, but in our experience, 2 to 4 works best. So you don't just push one task per core, you want to have a bit more of such tasks in the queue so that they are not slacking off the cores. And then, well, you need to check Ganglia UI to see whether your configuration, whether this number of threads and the sizes of the tasks, whether it actually can utilize your cluster well. It can look something like that. And so here the utilization is around 70%, which is not great, not terrible. We can get, ideally it's sometimes set to 80%, would be better. And so it depends, you can get there with some experimentation. And then you need to also run a performance test. So time, the duration. So in this experiment, we have tried to vary the number of threads, the number of batches that you have in parallel, and also the number of partitions into which you repartition your data. That means the sizes and numbers of tasks. And you can see that the shortest duration is somewhere around in this combination of like 8 threads and 16 partitions, or 16 threads and 8 partitions. So both of them are really comparable. And of course, you need to do some typical Spark optimizations, like the data should be cached before you start using this resampling and model fitting, because it's an iterative process. And also it, in our experience, helped that we didn't just cache it, we first persisted the data using checkpointing. And then after reading from the checkpoint, we then cached into memory. That proved to be the fastest solution, which really utilized the CPUs and didn't waste resources in I/O. So what are all the lessons that we have learned from this? What I have personally learned? And so I come from experimental background where we typically wanted to do inferential statistics to figure out whether some experiment works and not predict something, which is typical in machine learning. And Spark is actually seems to be better suited for machine learning than inferential statistics. And how to do inferential statistics in Spark? One way is to use bootstrapping, because you can do inferential statistics without quantification of the uncertainty, and bootstrapping can do this for you. But it's quite expensive, right? Compared to computing, for example, standard errors, it takes a lot of time. So in our clusters, it really can take hours, tens of hours sometimes. So you can also do parallelization in Spark. That was really interesting to me, because you often hear about Spark as being a parallel computation engine. And for these embarrassingly parallel problems, I really didn't know how to do it. And this multi-threading proved to be a way how to do that. Then I learned that shifting from p-values to these distributions really was a good idea, because the business users really love the outputs. They say that's one of the best advantages of our solution for them. They know with what probability it will help, how much. Then the core of factorial A/B testing is quite simple. It's just simple orthogonal factorial design and simple inferential statistics. But there are many interesting challenges in reality. So you have to deal with things like overlapping tests. They don't always start and end at the same time. There can be interactions between the tests. There can be funnels. You have to deal with outliers, with weird distributions of the data, with zero inflated metrics. And then the business user will ask you, well, can you still reduce the time it takes for evaluation of the test? So you then start dealing with variance reduction techniques and so on. And well, it pays off to really tackle these challenges. But if you want, then we will be happy to help you with that, because we have already went through this journey and we have experience with that. So thank you for your attention. And if you want to know more, then just drop me a line and have a nice day.